Hello, so in chapter 4, we're going to talk all about the atom. Early ideas about the atom came from the ancient Greeks, and they decided that matter could be best categorized as earth, water, air, and fire. They didn't know much about studying science like we do now after the scientific revolution, so their analysis was based mostly on observation. One of the great thinkers of the time, Democritus, had an idea that the atom was like a tiny indivisible particle. But this idea was kind of put to the side when Aristotle rejected the model, and it was not accepted for many years. But in fact, when we get to Dalton, we'll start to see that this model that was based on the scientific method was pretty similar to Democritus's idea. And this kind of, before I get into all the models of the atom we're going to talk about that built up over time, I want to just emphasize, one of the big ideas in science is that scientific models are the result of many scientists' work over a long period of time. So our current understanding of the atom, started with Dalton's model, which was a well-tested model at the time. But as new evidence came about and more testing occurred, the model gets refined. So Dalton was the first modern scientist in the early 1800s to work on the atom. And an atom is defined as the smallest particle of an element that has the properties of that element. In Dalton's model, there were no subatomic particles, so atoms were illustrated as circles, like in the upper right-hand corner. And atoms of the same element had the same mass, size, and properties. So there were different kinds of elements and different kinds of atoms, and different atoms, which ended up being different elements, have different masses, different sizes, and different properties. Thomson's work followed, from which he came up with the plum pudding model. Thomson did the cathode ray experiment, where basically he had some particles traveling through this vacuum tube here, and he noticed some deflection, so he concluded that there were subatomic particles, positive and negative, and he concluded that they are most likely scattered all throughout the atom, as illustrated in his model there. And it's called the plum pudding model because he said the particles are spread out just like the raisins in plum pudding, which is an English dessert. Rutherford worked to build on this model. So in his experiment called the gold foil experiment, he took a source of alpha particles. You can think of alpha particles like little tiny circles or beads that he fired at gold foil, or emitted towards gold foil. And what Rutherford kind of expected to happen was he expected that most of the particles would go right through with very little deflection, or maybe have a little deflection, when they hit one of the scattered pluses and minuses. However, when he did the experiment, he found that most of the particles did go through, but a few bounced back at pretty large angles, right? So if we kind of zoom in, here's what he, expected to happen, a little bit of deflection, some just going straight through. And what actually happened was most went straight through, but a few hit something and bounced off. So he concluded that since he was firing positive particles, there must be a bunch of positive particles in like a nucleus in the center of the atom that they were hitting. But also the rest of the atom was mostly empty space. So Rutherford's model has two conclusions to it, really. Number one, the atom is mostly empty space. And number two, there's a center core of positive particles called the nucleus. Bohr was the next scientist, and his model is really what we focus on here in high school chemistry. And he said that electrons orbit the nucleus in rings called principal energy levels. And the first principal energy level can hold up to 2 electrons, the second 8, the third 18, the fourth, we'll talk about this a little bit later, can hold up to 32. And since it's kind of like electrons orbiting around the nucleus, he said it was kind of like planets going around the sun, so sometimes this is called the planetary model. And here's an illustration of Bohr's model. So you can see we have the different energy levels, protons and neutrons found in the center. Note this is not to scale. The atom is still mostly empty space. Those electrons are very far from the nucleus in this model. As more technology developed, the Bohr model wasn't quite enough, so the quantum mechanical model, or the wave mechanical model, or the modern model is the most widely accepted model right now, in that it's the model we use to explain most things that happen in chemistry and physics. Now, we're going to use the Bohr model, like I said, because the Bohr model is a little simpler and it's easier to explain the topics we talk about in introductory chemistry. But the modern model, we'll just mention for a few minutes here, is based on this idea that those electrons are not spinning around like that. Those electrons are actually moving constantly, and they're in a location called an orbital. So you can kind of think of it like if you have the nucleus here, right? The electrons, the first two electrons are somewhere kind of always in this, we'll do this like this shaded space here. And that's would be called an s orbital, which we will talk about a little bit later. So we call that region where the electrons are expected to be found the orbital. Sometimes it's also called an electron cloud. And if you do a little more reading on this, you'll see that we can have different shape orbitals, S, P, D, and F, which again, we'll talk about a little bit later. So those are the models of the atom. And the big idea, again, that they were built up over time based on evidence, just like many topics that we study in chemistry and in science.